Today I'm going to talk about LeetCode question number 110, balanced binary tree. Given a binary tree, determine if it's height balanced. For this problem, height balanced binary tree is defined as a binary tree in which left and right subtrees of every node differ in height by no more than 1. Okay, every node. We can't just check the root here. Okay. So for example here, this is a valid balanced binary tree because over here, and for at least this node, for every node, I mean the height of its children differ by no more than 1. So for example here, height is 1, height is 1, they differ by 0. Here, height is 1, height is 2, okay, and they differ by 1, and also here. Okay, they differ by 1, and it matches the description of the balanced binary tree. But for this one, it's invalid because, okay, and this guy is valid here, this guy is valid here, this is 1, this is 2, okay, fine. And for this one, that's 1, and 1, 2, 3. 3 minus 1 is 2, and this violates the constraint, and this is not a balanced binary tree. So how we could go about this problem is, for each node, we could check the maximum height of its left subtree and its right subtree, and then same thing and then check if the difference is no more than 1, and then do the same thing for next node, left, right, check the difference, okay. Same thing for this node, left, right, check difference, but we do a lot of repeated work, okay? So for this guy, we're checking the height here, okay? And then for this guy, we're checking the height here. We're doing repeated work. So, and we're visiting each node multiple times. So we can try to visit each node at most once, okay? So what we're going to do is a post-order traversal, where post-order traversal of a tree means the children are visited first and the parents last. Okay. And for each post-order traversal, we're going to determine, at the very bottom here, like this is none, okay. Determine the height. So at the way bottom, determine the height. And this height is 0, 0, because 0 nodes go in none, okay. And then if we're looking at 7, and then we determine the very bottom height, okay, and then we bubble up, okay. Compare the heights, compare the difference of the heights of the left subtree and right subtree of 7, so 0 minus 0 is 0, doesn't violate the constraint, okay, and then we bubble up, and then what do we bubble up here? We bubble up the maximum height of the left subtree and right subtree, maximum of these two plus 1, okay? Why plus 1? Because look, these none nodes consist of 0 nodes, okay? That's a given. So when we bubble up the result here, we want to include this node, okay? So we have to do the max of the left, right, plus 1, okay? So if you do like 0 plus 1, instead of the 0 represents this, the 0 plus 1 represents this. And for 20, we want to look at this subtree here, okay? So that's why we do plus 1. Similar for 15 here, similar logic. We check the difference. Okay, 1 minus 1, 0, still doesn't violate it. And similarly for here, 9, okay? So for 20, the heights of the left is 1 and right is 1. And for 9, the heights of the left is 0 and right is 0, okay? So then we bubble up, okay? 2, 1 plus 1, 2, or sorry, max of L plus max of left right plus 1, okay, and max of 1 and 1 is 1, so we bubble up 2, and here we bubble up 1, and then we check 2 minus 1. Is that no more than 1? Yep, no more than 1. So now that we're at the root, this is obviously true. What about this case here? Okay, so we obviously know the left subchildren, right subchildren of here is 0, 0. Okay, valid subtree for these leaf nodes. And then we bubble up here. Okay, bubble up here, 1. So left is 1, right 1. Different, they're the same, so still a balanced binary tree at this point. Okay, similarly for here. Whoops. Okay. Then we want to do is bubble up plus 1, and we do the bubble up the maximum of left to right plus 1. Okay, max. We want the maximum, you know, just in case this is like R here, and then sorry, this is a node here, and we don't have the node here. Then obviously we're going to bubble up 2, and this is going to be 0. So okay. And then here, left is 2, right is 1. Okay, still okay. And then bubble up max plus 1, so 2 plus 1, 3. And then similarly for here, this left is 0, right is 0. This is a valid balanced binary tree at this node specifically. So then bubble up the max plus 1, 1. And then we see, oh, 3 minus 1 has a difference of 2, and we can differ in height by no more than 1, so therefore this is an invalid balanced binary tree, and we return false. Okay, and that's how we're going to go about it. We're going to use obviously depth first search, and this is going to be O of n time because we visit each node at most once. And since we have to output true or false, what we're going to do in a depth first search is not just return the maximum of left to right plus 1, we're also returning it as a tuple, so we're going to return max left right plus 1 along with a bool. Bool that's going to be like absolute value of left minus right less than 2. Okay, and what this bool represents is at this node that we just looked at is the absolute values of the left height and right height, or the difference between left height and right height, absolute, less than 2. If it's not, this is going to be false, and we're basically going to bubble up false to the top. And why do we do this? Well, if we know at one point, these should be arrows. Well, if we know at one point this was not a balanced binary tree, why do we want to keep calculating, you know, the height differences between the left and right of a node? Okay, we're just going to bubble up false every time, but it saves us some calculations. Okay, and that's how we're going to go about it. Okay, now to code it up here, so what we're going to do is define a helper recursive function, so root, and what we're going to do, so if root is none, return 0 and true. Okay, if root is none, then obviously the number of nodes we have so far is 0, and we're going to return a true tuple. Okay, and what we're going to do is do a post order traversal, so recurse the left subtree first, then right subtree, Okay. And now what we want to do is, okay, so we finally got those heights of the left and right subtree there. So now we want to check if absolute of left minus right is greater than 1, okay, or at, oh, sorry, this is actually a tuple, so 0, 0, where the 0th position represents the height, or left 1, which is the bool, is false, or right 1 false. Then what we're going to return is let's say -1 and false. It doesn't matter what we return here, okay? Every time we go up the recursion call stack, every time we bubble up, if these conditions are right, or if these conditions are met, doesn't matter what left or right is, and if these conditions are met, then we're just going to bubble up false, okay? Or else what we're going to do is if this condition is not met at all, especially this one, then obviously the binary tree is balanced at that node, so we're going to return max left 0 right 0 plus 1 and true. Okay. Yeah, that looks about right. So now we're going to call a recursive helper function and then return the tuple at position and return the bool at position 1 of this tuple. Okay. Yeah, it looks about right to me. I'll try running it. Okay. And I'll try submitting it actually. Okay, great, it works. Thanks for watching.